Yo, welcome back. All right, we are going to talk about today the derivative of a function. What does that actually mean? Pretty neat stuff here. So here we go. I'm just going to start out with a definition. You pick up a calc textbook and you look up derivative, and it's going to say the following: derivative of function f with respect to the variable x is the function f prime, whose value at x is given by. You can see this limit here, provided that the limit exists. Now, you should recognize this limit inside here, right? That's the limit of the difference quotient. So let's just kind of refresh our memory a little bit and sketch a little picture of what's going on. So if I go ahead over here and sketch a nice little function. So maybe my y equals f of x looks something like that. All right. What actually is just this part here representing? So the part without the limit. Hopefully you're saying that that's representing the slope of some secant line over an interval, right? It's the average rate of change over an interval. Now, what is the interval here? So when we did this the other day, it was from a to a plus h, and it was f of a plus h minus f of a. Well, okay, now it's f of x plus h minus f of x. So in other words, the interval is from some point x to some later point, although it could be previous if h was negative, x plus h. So now this difference quotient here is change in y's, f of x plus h minus f of x over x plus h minus x, right? The x's would sum to 0, and you just get h. So this here represents the slope of that blue secant line right there, okay? All right, so then what happens when I take the limit of it, right? So now if I take the limit as h goes to 0, remember what that does, that drives this point all the way over here. So all of these secant lines now end up approaching this limiting position of the tangent line, okay? So when we do this, right? That's going to be the instantaneous rate of change or the slope of the tangent line. Now, slope of the tangent line where? At x, where x is allowed to vary. So think about it. When you did it the other day, we had a number here, like 3, 4, 5, whatever it was. And at the end of the day, we got an answer for a slope. Well, now instead of there a number being there, there's an x. So your answer is going to have an x in it. So we say that basically, we write that your answer is representative of what we call f prime of x, right? So you're not just going to get a slope, so to speak, you're going to get a slope formula where you'll be able to put in whatever x value you want. That is called the derivative. The derivative is basically the slope producing machine, right? So because there's an x here, your answer is going to have an x in it. So now remember, there was kind of a couple of ways to represent that average rate of change. So I'm going to kind of go ahead and label this picture a little differently here. If instead of calling this x and x plus h, and be a little lazy and just kind of cross those out, right? And instead I call this a, like I did the other day, and I call this x. Now I'm going to get the slope of the tangent line at a, but if I'm allowing a to vary, my answer is going to have an a in it. So we say that's f prime of a. So this would be like a derivative with respect to a, so to speak. It's a little bit weird when we write it this way. We really should either just flip these and then get f prime of x, or just write as a goes to x. But for whatever reason, we accept this as the alternate form. But it's the same deal, right? This difference quotient would represent the slope of that secant line. And if I take the limit as x goes to a, this point moves over. I get the slope of the tangent line just now at a. So my answer would have an a in it. All right, that, my friends, is the derivative. So a couple of notes before we start rocking through some problems. Note, if f prime exists, we say that f has a derivative or that it's differentiable. So if we tell you that a function is differentiable, that means you're able to find a derivative for it. And so a function that's differentiable at every point of its domain is considered to be a differentiable function. Remember now how we were interpreting these limits above? Now we're calling it the derivative, but the interpretation is the same. So the derivative can be interpreted in two ways. F prime is the function whose value at x is the slope of the tangent line to the graph of f at x. All right, but you can also think of it as instantaneous rate of change. Okay, I like to think of the derivative as the slope producing machine. All right, so this function notation f prime of x now is going to represent your slope producing machine. Now the derivative is kind of interesting in that it was, calculus was discovered at different time periods and in different parts of the world, right? And we didn't have cell phones back then, so it's difficult for people to communicate and get on the same page. So there's two pretty much well-known accepted notations for derivative. One is what I've been showing you so far in this video, f prime of x, that is read f prime of x, right? You could also have y prime, right? Sometimes that we write it that way. We call that prime notation, and that came from Newton, right? But there's other notation that's acceptable, right? This right here, that would be read as dy dx. We don't really read it as dy divided by dx. We say dy dx, or better yet, the derivative of y with respect to x. And you can do it with anything. You can do df dx, dg dx, whatever, d whatever the function is dx. Okay, so that's a different style of notation. That was named after a different mathematician. That's Leibniz notation. All right. This final notation I like to refer to as command notation. So you'll have some function, and if you want to take, say, I want you to take the derivative of that, you put a little d dx out in front. So this would say, take the derivative of the function inside. That's command notation. These are actual symbols for the derivative. This is like a, hey, go ahead and find the derivative. All right, now it should make a little bit more sense when we get into it. So now we can evaluate the derivatives at various points, right? Because I might want to plug a number into the derivative. So the first thing here, that shouldn't surprise you. If you want to evaluate the derivative at some number a, then just do f prime of a. Evaluate that function at a. So that's just function notation. This might be new for you. When you use Leibniz notation, you would do the same type of thing, but you'd write dy dx, you do a little evaluated bar, and then a subscript wherever you want to evaluate it at. Dy dx evaluated at a. They are both symbols for finding the derivative and then plugging the number a into it. Okay. All right, so let's just do some practice here. So let's start with this first question. It says, find the derivative of the function f of x equals radical x. And I actually want you for the first time to use both definitions. So the main definition and the alternate form definition, or otherwise known as the alternate definition. All right, so how do we do it? So as soon as it says find the derivative, you're like, oh, I have a definition of the derivative, right? I have a formula for that. F prime of x is going to equal the limit as h goes to 0 of f of x plus h minus f of x all over h. That is the definition of derivative. If they ask you to find f prime of x, this is what you do, right? Every single time. So now you have to do this stuff. So in other words, let's go ahead and do f of x plus h. So how do I do f of x plus h? I'm going to put x plus h in the function f where I see an x. Well, I see an x right there. So when I do this evaluation, I get radical, right, x plus h. I do not get radical x plus h. That's something different, right? That would be f of x, close the parenthesis, plus h, right? This is f of x plus h. So all of x plus h goes in f where there's an x, okay? All right, rock and roll and keep going here. Then I have the minus, and now I just have minus f of x, but f of x is right here, right? So when I do minus f of x, I just do minus f of x, and then all over h. And so it's a limit question. So the first thing you do is you chuck 0 in for h. You get radical x minus radical x, that's 0, over h. That's going to 0, that's 0. You get an indeterminate form. So who remembers what to do when you're doing a limit with radicals and you get an indeterminate form? Hopefully you are saying multiply by the conjugate of the expression where the radicals are, which would be in the numerator. So I'm going to multiply this entire numerator by the conjugate of this expression. So that's radical x plus h plus radical x, and then over itself. You have to have the over itself bit because it really means you're multiplying this fraction by 1, and that means you're not doing anything to it, right? You might change the way it looks, but you're not going to change its value. All right, so now what do I got going on here? I have the limit as h goes to 0. So radical x plus h times radical x plus h, that's just x plus h. The beautiful thing about multiplying by conjugates is the outer product and the inner product in the distribution will sum to 0. And then you just get minus radical x times plus radical x, that's minus x. So that's what I get when I multiply out the top. On the bottom, it's going to behoove us not to distribute. So I'm going to get h times radical x plus h plus radical x. And hopefully good things happen, and I think you can see that they do, right? The x's are going to sum to 0, so I'm going to cross them out. which means I just have an h in the numerator now, right? So it's h over. So you're like, all right, well, then there's an h in the bottom and it's connected with multiplication. Now maybe you see why I didn't want to distribute it, right? So I can cross out this h and that h, right? They're like factors. I can divide them, put little ones behind, and that would be my simplification. So I'm going to clean this up for the purposes of the video, and I'm going to get now the limit as h goes to 0, because I have not taken it yet. Of up top, I just get 1 over, and on the bottom, I'm going to get radical x plus h plus radical x. So now I'm going to put 0 back in for h. So that's radical x plus radical x. How many radical x do I have in the bottom? Hopefully you're saying 2. So you get 2 radical x. So you get, I'll kind of write it side by side, you get that f prime of x is going to be 1 over 2 radical x. What the heck is that? That is your derivative. That is your slope producing machine. You can't just say it's the slope. It's the slope producing machine. So what does that mean? That means it's a formula for the slopes of any tangent line at x. So if you want the slope of the tangent line at 2 on f, chuck 2 in there. You want it at 4, chuck 4. You want it at 7.3, chuck 7.3 in. Okay, so that's what this guy is. This is your derivative or your slope producing machine. All right, now we normally don't do the same problem twice, but here, just to kind of drive home the fact that it can be done two different ways, it wanted us to use both definitions. So we're going to redo this problem now using the alternate definition. So I'll do that in blue. So f prime of, in the alternate definition, most textbooks, not all, have it in terms of a. So f prime of a. So that's going to be the limit of, if you remember, it's f of x minus f of a over x minus a as x goes to a, right? That's the definition. That's the alternate definition. Again, this difference quotient is the slope of the secant line or the average rate of change. And when you make the point x go to a, you get the slope of the tangent line or the instantaneous rate of change. All right, so how do we do it? You're going to do it very similarly, right? So what is f of x? Well, f of x is radical x. I'm not going to go with the colors here. I think you can figure it out. Minus, what's f of a? Well, that would be that. All over x minus a. So what do I do now? I'm going to chuck a in for x. So I get radical a minus radical a. That's 0. Bottom, I get 0. You're always going to get 0 over 0 initially when you do the definition of the derivative. So I got to try something. Well, what can I do? Well, actually, I can do exactly what I did up here, right? If I have 0 over 0 with radicals, I can multiply by the conjugate of the numerator over itself. That would be one way to do it. Now, I just showed you that technique. So I'm going to show you another way to do it. All right. How else could I do this? Well, you know what? I'm going to look at the bottom and I'm going to say, I'm going to treat that, even though it's not a difference of perfect squares, I'm going to treat it like a difference of perfect squares, like x squared minus a squared, and factor it. Now, it's not x squared minus a squared, it's x minus a. So then how would I factor it? Well, the algorithm is basically the same. It's the square root of the first thing plus the square of the second thing times square of the first thing minus square of the second thing. So in other words, the bottom can get factored into radical x minus radical a times radical x plus radical a, right? If you distribute this out, radical x times radical x is x. The outer and the inner products, they're going to sum to 0, minus radical a times positive radical a for appropriate values of x and a, I should say. That's just going to be minus a, and then it works out. So this factorization is going to work. So now why is that good? Well, this factor and that factor, they're exactly identical, right? So they divide out. So now I just get 1 over radical x plus radical a. And so I'll clean it up. Limit as x goes to a of 1 over radical x plus radical a. And now I'm substituting a in for x. I get radical a plus radical a in the bottom. That's 1 over 2 radical a. And you're like, oh, that's exactly what I got here. Now I know it's weird because you're like, okay, it's in terms of a. F prime of a is 1 over 2 radical a. Well, you can just transfer that to, if f prime of a is 1 over 2 radical a, that means f prime of x is 1 over 2 radical x. Okay? So this is using the alternate form of the derivative. Okay? All right, so now, what do we got going on here? So now B says, go ahead and find f prime of 1 and f prime of 9 and then interpret their meaning. Well, you have the slope producing machine, right? You have f prime of x. So if you want, I'll do b over here. If you want f prime of 1, you simply have to put 1 into the slope producing machine. So you're going to get 1 over 2 radical 1. That's just going to be a half. Okay? And if I want, move this, can I move this guy? Nope. If I want f prime of 9, right? That's just going to be 1 over 2 radical 9. So square root of 9 is 3. It's going to be 1 over 6. So that's us evaluating the derivative at 1 and 9. Now, interpret the meaning. What the heck does this mean? This means if I was to look at the graph of radical x, all right, so I'm going to do a rough sketch, right? We all know radical x looks something like that. The fact that I got f prime of 1 equals a half means that if I was to go over to 1 on this graph and draw in a tangent line, the slope of that should be up 1 over 2. That certainly seems reasonable, okay? Likewise, if I was to go all the way over to 9, right, and draw in a tangent line, the slope of that should be up 1 over 6. You can see it's not going to be as steep. So both of these seem reasonable. So when it says interpret their meaning, it's basically wanting you to say that it represents the slope of the tangent line on the graph of f at x equals 1 and x equals 9 respectively. Okay? All right, last part of this question is write the equation of a tangent line. All right, so you're going to want to write this down, all right? Hopefully you remember the point slope form for the equation of a line. It's y minus y1 equals m times x minus x1, right? That is old school algebra days. That little formula will get you the equation of any line provided you know a point, and the point here is the x1 and the y1, and then provided you know a slope, and obviously that's the m. So now if I want the equation of the tangent line at x equals 1, I got to get the y value because I need the point. So how would I get the y values? Like how would I get the y value right here? Well, it's f of x equals radical x. So I would just plug 1 into that, right? It would literally just do f of 1, not f prime of 1, f of 1. That's the y value. And if I did that, I'd get the square root of 1. That's 1. So the point is 1, 1. So that's my x. That's my y. You can see that right there. Okay? So now what's my slope there? Well, the slope of my tangent line is not f of 1. It's f prime of 1. That's what this means. This means slope of the tangent line at x equals 1. So f prime of 1, we just did that. That was a half. So I have the slope of my tangent line. So now if I want the equation, I just use the point slope formula. So it would be y minus 1, this one, by the way, right, equals 1 half times x minus 1, that one. Maybe I'll color those up. This is that one. This is that one. Okay? And now put a happy cloud around it, guys, because that's it. You don't need to be a hero and solve for y. That is a perfectly good equation of a line. In fact, this is the equation of the tangent line. So understand that sometimes they're going to ask you just for the slope of this tangent. So in other words, I just want to know what the slope of this tangent is. Sometimes that's the question. If that's the question, you're just saying a half. But sometimes they'll want, since it's a line, they're going to want the equation of that line, right? And that's how you do it right here, point slope formula. Now, do you ever have to solve for y? Well, hey, listen, it might be a multiple choice. If it's a multiple choice, the choices might have y solved for. So then, yeah, you're going to have to know, obviously, how to do that. It might be you want to check the answer in the back of the book and they solve for y. So you have to know how to manipulate it. But if it's a free response and they're asking you for the equation of the tangent line, then you can leave it in that form. All right, so we did a lot in that question. All right, so let's rock and roll. Let's go to the next one. All right, it says if y equals 1 over x, find dy dx. So again, this is just now testing you on, were you paying attention when I talked about notation, right? This is the symbol for the derivative. This is like f prime of x. So now instead of saying f prime of x equals, I'm just going to follow the notation. I'm going to say dy dx equals. How do I do this? I use the definition of the derivative. Now I have the choice. I can use the alternate form or I can use the definition of the derivative, the one with the x plus h in it. All right, you know what? This time I won't go alternate. I'll go with the main one. So it would be the limit as h goes to 0, and then it would be f of x plus h minus f of x all over h. That is the definition of the derivative, right? So that's always what you start with. Since they said find dy dx, instead of writing f prime of x equals, I write dy dx equals. That shouldn't freak you out, okay? So now, what do I do? Well, I'm going to actually start to evaluate. So what's f of x plus h? Well, that means put x plus h, right? Put x plus h in the function f, where in this case y. I probably should have called this y of and y of. I didn't, so maybe I'll just cheat and be like this. Shame on me, but it would have been cooler if I wrote y of x plus h and y of x, but whatever. I put x plus h in the function where I see an x. Well, I see an x right there. So then I'm going to write 1 over x plus h. All right. And then it's going to be minus f of x. Well, my f of x is just this. It's 1 over x. And then all over h. Directly substitute 0 in for h. I'm going to get 1 over x minus 1 over x. That's 0. Bottom I get 0. Indeterminate form. What do? I have fractions. There's a whole bunch of different ways to do this. You can multiply by x times x plus h if you want. That's a solid way to do it. You can also do what we call the fastest technique known to MANN, M-A-N-N, right? My old calculus teacher, and basically subtract these fractions. And you know what? In honor of him, I'll do it that way. So here we go. We start in the top left corner, 1 times x, that's x. Always keep the sign. Multiply on the bottom, from the bottom left to the top right, so on the other diagonal. So that's going to be x plus h times 1, which is x plus h, but there's a negative in front, so I am going to be awesome and distribute the negative right off the bat. And then all over what I get when I multiply the two bottoms, which I'm not going to distribute. And oh, by the way, now all of this is divided by h, but then that would give me this fraction sandwich, and no one likes fraction sandwiches, right? So I don't want to write all of this divided by h. So I know that dividing by h is like multiplying by 1 over h. All right, so I went about simplifying it that way. So now what happens here? Hopefully good things. All right, so the x's are going to sum to 0. So that's great news. So now that means that you're left with just a negative h up top and a factor of h on the bottom, and they are connected with multiplication. So I'll cross that out, make it a 1, and then emphasize that when I cross this out, it's going to be negative 1. So if I spruce this now, I'm going to get the limit as h goes to 0 of negative 1 over x times x plus h. And stop there for a second in case you were going bananas about how I went from this subtracting fractions to this. Remember, guys, it's nothing crazy, right? Really, all I did is I got a common denominator. So I multiplied this by x over x. I multiplied this by x plus h over x plus h. My common denominator was x times x plus h. And then I distributed the negative and combined the top, right? We just called it the fastest technique known to man just because it's kind of what you do. Not always efficient because sometimes you have to simplify if there are common factors down here, but when there aren't common factors, it'll always be efficient. All right, so anyway, getting back to this. Now I am ready to go ahead and chuck 0 in for h. And when I do that, I get x times x in the bottom. That's going to be x squared. So I get negative 1 over x squared. So now what is that? The fact that I got dy dx is negative 1 over x squared. That is my derivative. So this is my slope producing machine on the graph of 1 over x, okay? So now when it asks me to do this, dy dx at x equals 10, that is like asking to do f prime of 10. Whereas this here is like f prime of x, this here is like f prime of 10. In other words, plug 10 into your derivative. Well, I have my derivative right there. There's my slope producing machine. So I end up getting negative 1 over 100. Okay, what the heck does that mean? That means that if I was to look at the graph of 1 over x, which we should all know what that kind of looks like. I'm not going to bust out Desmos here. I'm going to actually do a quick cheese ball sketch. So 1 over x is going to look like that, right? A little hyperbole. If I was to come over now to 10, so x equals 10 on this graph, and draw in a tangent line, right? We are saying that the slope of that tangent line is going to be down 1 over 100. Now, that certainly seems reasonable, right? That it's not going to be that flat. Obviously, I'm not drawing this thing to scale, but it certainly seems reasonable that that tangent line would be down 1 and then over a bunch, okay? In fact, it is. That's what it is, okay? All right, rocking and rolling. We got a lot going on in this video, so we're going to keep going after it. All right, 3. It says find the equation of the line that is tangent to the graph of 2x squared plus 1 at x equals 1. Right? We'll forget about part B for a second. So as soon as I see equation of a line, I am thinking, right? This tells me to think point slope. Y minus y1 equals m times x minus x1. Now, in order to use the point slope formula, I need a point and a slope. So maybe I'll get the point first because it's pretty easy. We want it at x equals 1, right? That's the x value. So to get the y value, I would just do f of 1, right? So 2 times 1 squared plus 1. 1 squared is 1 times 2 is 2 plus 1 is 3. I get 3, right? So my slope of my tangent line now is up next, right? So I don't know why I just jumped up there. So I have the point. Let me write the point 3. This is one of those situations where I'd redo the video just because I said that. But now that I've done 8 billion of them, I'm not redoing it. All right. So we have the point 1, 3. So basically, we want to go ahead and look at this graph. And at the point 1, 3, write the equation of the tangent line. So you got the point for the point slope formula, but it's called the point slope formula, right? So what else do you need? You need the slope. So how do you get the slope? Hopefully you're saying find the derivative. Okay. So let's do that. So there's kind of 2 ways to approach this now, right? I can find the slope producing machine and then chuck 1 into it, or I can use the definition of the derivative and chuck 1 in it right from the get-go. And you might be saying, like, what do you mean? Well, let's do the first thing that I suggested. So let's find f prime of x. So again, do you have a definition of the derivative? You certainly do. It's the limit as depends on what I want to do now, right? So do I want to do the alternate or the regular? I'll go back to the regular. So limit as h goes to 0 of f of x plus h minus f of x all over h, right? So that's the definition of the derivative. So now I start to evaluate. Limit as h goes to 0, what the heck is f of x plus h? Well, I have to plug x plus h into the function f where I see an x. So it would be 2 times x plus h squared plus 1. That's f of x plus h. Okay? And now I have minus f of x, so that'd be minus f of x. So if I just wrote this, that's wrong because it didn't say minus the first part of f of x. It said minus all of f of x. So hopefully you're saying that since your function is more than one term, you need to have that in there. Right? You need those parentheses. And then all over h. So again, not that you'd maybe want to do it, but if you chucked a 0 in now, right, you're going to get 0 over 0. So you have to try something. So the something to try is basically just simplify, multiply all this out. So I'll start with order of operations. Let me multiply out x squared plus x plus h quantity squared, and then distribute the 2. So x times x is x squared, distribute the 2, 2x squared. Okay? X times h, xh, h times x, xh, right? I have 2xh multiplied by 2, that's 4xh. If you're not following, just take the time and write this twice and distribute it. H times h is h squared times 2, that's 2h squared. Then I have plus 1, then I have negative 2x squared, and then if I distribute this negative, I get minus 1. All of this is over h. So now, what happens? Hopefully good stuff. So here's a 2x squared, here's a minus 2x squared. That's going to sum to 0. That's awesome. All right. Here is a plus 1. Here's a minus 1. That's going to sum to 0. That's awesome. So if I rewrite what I have now, I have limit as h goes to 0. Now take a look at this. Every term up top has an h. So I'm going to factor out that h. Right? I could pull a 2 out, but I don't want to. I'm just going to pull the h out. And then I'm going to get 4x plus 2h over h. And the reason why I factored that h out is because hopefully you can see it. Now I have it connected with multiplication. I can cross out these like factors, put little ones behind. So now I'm ready to go ahead and chuck a 0 in for h. So that would wipe that out. I would just get 4x. So f prime of x is just going to be 4x. So what the heck is that? That is my slope producing machine. That is not the slope. That is not what I'm putting in there. That's the machine, right? I want the slope specifically at x equals 1. So when I go do the slope here, right, and I write my nice little notation, m tan, I need it to be f prime of 1, right? The slope at that point. So I would come over here and be like, all right, well, what is f prime of 1? Well, it would be 4 times 1. It would be 4. So this is the slope producing machine, right? Slope producing machine, otherwise known as a derivative. And this is the slope at x equals 1. And that's what I need when I want to write the equation. Okay? So now if I come over and put everything together here, think about it. I'm good to rock and roll, right? It's going to be y minus 3 equals 4 times x minus 1. All right, oops. Clean that up. I don't know how that happened. All right. Boom. All right, there you go. Put a happy cloud around it. And what does that represent? That represents the equation of the tangent, right? And then specifically at x equals 1. So if I was to go ahead, and I'm going to do a super, super, super rough sketch here, right? But if I was to go ahead and rough sketch this thing, right? I know it's a parabola. I know it's been shifted up 1, right? So this is kind of like the idea. Okay, so there it is. So there is f of x. And now what I just did is I went ahead and I found at the point 1, what we get? 3. So at this point right here, we not only found the slope of that tangent, but now we found the equation of that tangent. Okay, and that's exactly what we are finding, which is pretty neat stuff, to be quite honest. Okay, all right, so now there's one thing that I did want to say here is, all right, we did it by finding the slope producing machine and then chucking 1 in. I like doing that. That's a very efficient way to do it. But if you wanted to, you could have did what we've done in the past, which is, what if you just wanted to find the slope of the tangent line specifically at 1? Well, you'd use the same thing, just instead of putting x here, you'd put 1. So in other words, guys, f prime of 1 is the limit as h goes to 0 of f of 1 plus h minus f of 1 all over h. And you could have done it that way too. And it just would have worked out that when you did this, you didn't get a machine. You just end up getting 4 when you simplify it. All right, so understand that it can be done that way, but this is more efficient. All right, so now you're like, man, you didn't leave much room for the equation of the normal line, right? Well, that's good news because we don't need much room for that. So first off, what is a normal line? All right, you might not know. So a normal line is just a line that is perpendicular to the tangent line. So if I was to sketch that in right here, I would draw a little right angle symbol right there, and then I would label that the normal line. So all a normal line is a line that is perpendicular to the tangent line, goes through the same point. So you're like, all right, well, if I want to write the equation of the line, I have the point slope formula. It's the same point, right? What would the slope be? Right? So let me do this right here. So for the normal line, what would the slope be? Well, what do you know about perpendicular lines? They have negative reciprocal slopes. So the slope of the normal line, which we can symbolize m perpendicular, m perp, right, is just going to be the negative reciprocal of that. So it would be negative 1/4. So when I use this now with the point slope formula, it's going to be the point's the same, right? We're still going through that same point. So it's going to be y minus 3 equals negative 1/4 times x minus 1. And that would be the equation of the normal line. All right, so I'm going to stop there because it's a pretty long video and come back and continue with the other problems.